When an object moves through a fluid, it experiences parasitic drag. This can be broken up into viscous pressure drag and skin friction drag. Skin friction drag comes from the roughness of the object. The rougher the object, the more drag force will be generated. As the fluid passes over the object, a boundary layer is formed, which also increases the drag force. As the Reynolds number and velocity increase, the skin friction drag will increase. Pressure drag emerges from the shape of the object and how the shape is oriented in relation to the direction of flow. Generally, the more cross-sectional area that is exposed to the flow, the larger the drag force generated. As the velocity of the fluid increases, the amount of pressure drag will also increase. Although the drag force will increase with an increase in velocity, the coefficient of drag could actually decrease due to the inverse relationship between the force and the dynamic pressure in the coefficient of drag equation. The purpose of this experiment is to quantify the effects of the viscous pressure drag. Our team will place a cylinder in the wind tunnel and measure the force of drag at 24 different pressure taps, spaced evenly around the circumference. The Reynolds number and coefficient of drag will be determined for each test run. Then, a patch of roughness will be introduced at the point where the flow separates, and similar data will be recorded. First, the accomplishments of the team were laid out, so each member knew what was needed in the lab. The wind tunnel is a large structure that has three main areas inside of it. The first being an inlet that pulls in the air. A 10 centimeter thick honeycomb air filter maintains a laminar flow. After that, there is a test section where the parts and models are placed for analysis. This is where our cylinder was placed. This chamber has a small cross section and speeds up the wind flow inside for analysis. Finally, there's the fan diffuser system, which is the driving force behind the wind flow inside, as well as the component that condenses the air into streams. An inspection of the test chamber showed no immediate defects. After following the checklist, each member of the team took various positions throughout the lab. Two members were handling the spotlight and laser, two members were videotaping, and one was running LabVIEW. After three initial runs of 150, 400, and 650 RPM, the team attached Velcro strips to energize the boundary layer. The tape strips were placed at the points where the team believed the boundary layer separates. This was measured to be plus or minus 50 degrees from the horizontal. The test was run again at the same RPM values.
This plot shows the difference in coefficient of pressure around the cylinder. The black line is a theoretical solution for inviscid and incompressible flow. This solution differs from the real flow because it states that the cylinder experiences zero drag force. Since our system forms the boundary layer, it will experience recirculation of flow when separation occurs. The difference in pressure across the cylinder will result in a drag force in the direction of flow. For our test, the data has a general shape of the theoretical solution. The blue line shows the results of our test without sandpaper in place to trip the flow. This line shows coefficients of pressure that are greater than 1, which is not within the range of accepted values for incompressible flow. In cases of compressible flow, it is possible to achieve coefficient of pressure greater than 1, but this would not be possible in our low-speed wind tunnel. These values could be due to error in our collection method or interpretation of the raw data used to calculate coefficient of pressure. Again, the coefficient of pressure around the cylinder follows the general shape of the theoretical solution. As we increase velocity, our pressure begins to decrease. This is due to the increased vorticity of flow that causes earlier boundary layer separation, so not as much pressure is experienced by the cylinder. Similar to other graphs of pressure, we notice a jump at ports upstream of the flow. This makes sense because these regions of the graph also show the largest difference in pressure between test situations. We would expect the non-stripped flow to have a higher pressure because we are forcing the boundary layer to separate earlier, which decreases pressure across the cylinder. At our fastest RPM test value, the data still holds the general shape of the theoretical solution and follows a trend of decreasing pressure values. Another trend shared by all three speeds is the lack of symmetry of our lines that is seen in the theoretical solution. The plots are not perfectly symmetric due to a variety of reasons, the primary ones being the fact that flow is going from one side to the other. Therefore, on the front half of the cylinder, you have a formation of boundary layer, as well as separation of that boundary layer as you move across the cylinder. Theoretically, the cylinder should not have drag due to symmetry in the y direction, but in our experience, we see drag due to the imperfections in our system. We have systematic errors in the wind tunnel, like electrical conversions of the reading into data and holes in the wind tunnel messing up the flow.
Here's an image of streamlines that can show the differences between high and low RPM. At picture A, we can see that in low RPM, the boundary layer still remains attached to the cylinder. And in picture B, in high RPM, we can see that the boundary layer gets detached and then vortices are generated. Surface roughness. More surface roughness would cause the flow to stay less attached. The boundary layer would start building up earlier, and the fluid flow over the cylindrical surface would be more turbulent. This is the reason why a tape was used at the second part of the lab and forced the boundary layer turbulent flow to start at the tape location. Is the flow two-dimensional? The flow in the middle of the cylinder is not two-dimensional. There was some fluid flow that was traveling across the length of the cylinder. It would be easily detected if we had made the same test with surface tufts placed accordingly over the cylindrical surface. It might not be fully visible from the video, but if the recording was from a top view, it would be easier to be seen. There are some vortices on the wake that appear to travel parallel to the cylinder. The three-dimensional fluid flow over a cylinder can be captured by a CFD simulation, as we can see in the next image. Here we can see that in the middle of the cylinder there is a three-dimensional fluid flow. And in the next slide we can see a surface tufts test that can capture 3D fluid flow. We can see some of the tufts are traveling backwards.
We would want to treat the center of the panel as the pressure tap. If we thought of each point as the center, we would be creating stagnation points directly in front of the pressure tap, resulting in very incorrect numbers. In addition, we want the normal component of the flow velocity to be 0 at each pressure tap for our calculations. If we have our pressure taps on the corners, that could be an influence. And as for the Reynolds numbers for our tests, at 150 RPM, it's 3.165, at 400 RPM, 9.124, and at 650 RPM, 15.064. For this plot, we calculated the total drag force experienced by the cylinder by summing up all the individual pressure forces in the x direction read from 25 ports. We end up with 6 values for the coefficient of drag, which are in the accepted range, which is coefficient of drag is greater than -1 and less than 1. We then plotted the coefficient of drag at each RPM value. We see that the coefficient of drag follows the same trend for non-tripped and tripped flow. It decreases as velocity increases. This makes sense due to the equation we use to calculate the value. We divide by velocity squared, so as velocity increases, the calculated coefficient value will decrease. For non-tripped flow, the coefficient of drag was overall higher than what we calculated for tripped flow. And this makes sense because we would expect the force on the cylinder for tripped flow to be lower than the non-tripped. Since separation occurs sooner for a tripped flow, there is less force on the cylinder. And the difference between total drag pressure for tripped and non-tripped flow increases as RPM increases.
The graphs have the same pattern as the optimal periodic one. However, they seem slightly shifted to the right. This can be due to the orientation of the cylinder and at the exact location of the pressure ports. There must be a tolerance in the degree accuracy. Group members came in and out of the test chamber in order to apply the surface tape. There is a high possibility that they accidentally displaced the cylinder enough in order to cause false readings. In addition, in order to create the plots, we use the mean value measurements for each port. The graphs would appear closer to the optimal if we had more data points and ran a regression line. Another source of error is the fact that we did not calibrate our pressure reports before we started the test. That, and also the rounding error due to machine error, has contributed to the tolerance of our data readings.
In order to have an idea of the accuracy of our data, we found the standard deviation of all 200 data points for each speed and test parameter for all the ports. These graphs reveal any error that may have resulted from the collection method. From these graphs, the ports upstream experience more variance in the data collected. This area of the cylinder is experiencing a stronger force than other ports, so this increase in standard deviation may be caused by provided instruments to collect pressure data. At higher RPMs, wind is hitting the cylinder with more power, therefore causing it to bounce off like water smashing against a rock, where at lower speeds this doesn't happen. The trip tape standard deviation follows the same trend, but has a giant spike, which could be a systematic recording error, or it could be where flow is the most turbulent along the cylinder. Overall, trip tape has more deviation between measurements because of us breaking up the boundary layer before most of the ports. The Strohal number is a numerical explanation of visualizing flow. This photo shows a vortex separation in the air flowing around the cylinder. To calculate the Strohal number, you need to know how many frames per second you are shooting your video at, and also examine the video and see how many times the airflow actually separates per every second. And you can actually see this if you slow down the video enough. The text sort of walks through one calculation, and that final calculation you see is frames times length all divided by velocity u to get your Strohal number. The values we calculate at 150 RPM make sense, and at higher RPMs they don't make as much sense. At these higher RPMs, it's harder to see vortex separation because the airflow is so quick. It could also be from personnel error or not having a good enough frame rate with the recording abilities of an iPhone. With trip tape or not, there is no effect on the Reynolds number, and there is the same vortex. There is a small difference in the Strohal number, and this is due to different velocity readings. Referring to the rocket displayed outside SpaceX headquarters, yes, it does have a cylindrical shape, but I want to be careful about distinguishing between a purely cylindrical object and one with a rounded nose. A cylindrical object will have more drag, or a higher drag coefficient, than one with a rounded nose, such as a rocket. Examining a palm tree, yes, there is a cylindrical shape, but the surface is not at all smooth like it is on a rocket. The aberrations on a palm tree will increase the drag because drag depends on flow in the boundary layer, and the boundary layer occurs exactly where the aberrations are, so the surface is extremely important to an object when examining the airflow. Yes, roughness of the surface just depends on what material is used, but what affects behavior and how much drag exists, the shape and size of the surface and object is critical. Reynolds number depends on characteristic length, so if the diameter of the sphere is different than the length of the cylinder, I think Reynolds number would change.
In this experiment, our team wanted to visualize the flow separation on a cylinder at different Reynolds numbers. We wanted to show that as Reynolds number increases, the coefficient of drag decreases. In addition, the team wanted to trip the boundary layer and track its effects on the force of drag and the coefficient of drag. We attached Velcro at the points at which we believed the flow separates, which was plus and minus 50 degrees from the horizontal. We then ran the same tests. We only noticed a slight drop in the coefficient of pressure, which is to be expected. However, the coefficient of drag decreased significantly when comparing runs at similar RPM values. The coefficient of drag decreased, on average, by about 13/100ths. This is a significant amount for a test at our scale. This fully proves that by adding a rough surface and tripping the boundary layer, one can decrease the coefficient of drag. Going forward, we would like to see the effects of adding even more Velcro to the cylinder. If we added more Velcro behind the existing piece, could we get an even lower coefficient of drag?